So my name is Vishal Persaud, and I'm just here to present part of our research at FIU and the MMA department in collaboration with the University of Ghana as well. Optimizing hydrogen production using physics-informed neural network. Now, this morning session, we had someone did machine learning, LiDAR, and whatnot. But the buzzword right now in the world is hydrogen. It's a clean energy, offers clean energy between now and 2050 as we advance the path to net zero. We're currently producing most of our hydrogen from steam methane reforming, and we have about 8 to 12 kilogram of CO2 per kilogram of hydrogen. How can we reduce that? The US is investing a lot of money in its initiative, the 111 initiative, of producing 1 kilogram of hydrogen costing $1 in the next decade. Now, from this, we see that we can approach it in two ways, either by pyrolysis of biomass or natural gas. Now, natural gas is synonymous with any oil and gas producing nation, especially in the Caribbean, Trinidad, Suriname, and Guyana recently. All the natural gas there is flared, but we also have an abundance of biomass. So pyrolysis, what is it exactly, as I go into? It is a thermal degradation process in the absence of oxygen in the presence of a catalyst to produce three things, either a gas, a bio-oil, or a biochar. Now, all of these are very valuable. Now, for our research, we focused on producing hydrogen. And one of the byproducts is biochar, which can be used in our agricultural sector as well. Right? So we see that it is a method of producing sustainable hydrogen. It can offer energy security and as well as waste management. Now, catalytic pyrolysis can be used with any kind of organic material. So we can even apply it to waste plastics to produce, to break up the polymers to produce hydrogen as well for our focus. Now, even though it is a process like this, it is still at the lab scale. And getting it commercially or at scale would require a lot more research into it, especially when you require a catalyst to work for about 7,200 hours to produce the energy needed to power a small community, to produce the amount of hydrogen. So why not look at the age in technology? We are in an age of technology. So we're proposing to use machine learning to create predictive models that can help us optimize our hydrogen production from catalytic pyrolysis. What parameters, what catalyst formulation, and how long does the process needs to be so that we can get enough hydrogen to power the future. So machine learning, as we learn, is a part of artificial intelligence that use statistical data, and we've heard mentioned. Data is something that is lacking across a lot of our regions. Getting that data for this process is also kind of a challenge in the research, how it's going. So it uses that statistical data to create predictive models that can inform our experimental design. Now, this morning we learned about different models, random forest regression, but you're wondering, what exactly is a physics-informed neural network? It is an artificial neural network, which is a classic machine learning model, but we impose physical laws that are part of the process. So for pyrolysis, it is the mass transfer of utilizing so much biomass to getting so much byproduct. It is also heat transfer. And for our process, we imposed a small temperature gradient law to kind of see if we can predict better hydrogen production from the same amount of data. And as I mentioned, there is limited data set. So our methodology was simple. Gathered high quality data, even though and I will tell you exactly how much data set we have so far. Evaluate the data, as in we pre-process it. We standardize it, we normalize it so that we make the model robust, a little bit robust to outliers. And then we choose specific features from the process so that we can optimize to get hydrogen production. So features like at what temperature does pyrolysis occur? So generally pyrolysis occurs between 500 to 1,000 degrees. That's a wide range in temperatures. But how can we reduce our energy consumption while producing hydrogen? And by optimizing the temperature of the process, we can do this. Same with the residence time, the type of catalyst we use, and even going down a little bit more into the chemistry, the calcination temperature of the catalyst when we're developing it. So in our model, we use 70% of the data that we collect to train the model. The model can't learn on its own. We need to train it, and then it learns. So we use 70% of the data to train the model with these specific features. Then we test the model against 20% to see how it performs. And then we optimize it to give better performance by tuning what we call hyperparameters within the machine learning model. Then to see that, okay, our model can predict as we train it, we test it against 10% of data it has never seen. And because of that, we can see when we test the model, the actual versus the predicted values, utilizing a physics-informed neural network, we get about 83% accuracy. In previous model, and I'll show you in one of my graphs, how we compare it to classical models to what we call the physics-informed neural network. We reduce the mean absolute error overall and the mean squared error from 159 data points. Now, 159 data points in a machine learning model is very small. But because collecting data is a challenge, we work with what we have for now as we improve our data set. So you can see in our bar graph how we predict. A lot of it is very close, but there are outliers still that even though the physics is there, utilizing better physical laws, maybe even utilizing 4 years heat transfer conduction law may give us a better model. That is something that we're looking at for the future. So, bringing us now to how do we actually optimize it from an experimental point of view. Using machine learning models, we can see what features affect the production of hydrogen. And you see from here the support of the catalyst or what. So in our study, we've utilized nickel-based catalyst. So nickel loading is important, but also what support is there. So let's say like CNT or aluminum or I think calcium oxide, whatever support is there, it also plays an important role. We also see that temperature plays an important role in the process. So understanding these relationships helps us to optimize the hydrogen production from this process. So as I mentioned, I wanted to compare how classical machine learning models such as regular artificial neural networks or a random forest regression model compares to a physics-informed neural network. And as we see with the same data, because we are imposing this physics on it, we make the process more realistic, more applicable and practical. And because of that, we can now scale the process. And as each model is interpreted and we add data to it, we get improved accuracy. The ideal accuracy, if we get between 0.95 to 0.99, ideally, in an ideal world, 100 would be best, but we're all researchers. We won't ever get 100. But we can get informed and insights into how to optimize this process. Now, my colleague talked about solid oxide fuel cell. There are many different applications of how to produce hydrogen, electrolysis. But as those technologies are still in some of its infancy, we need something to bridge us between in the near term, in a sense. So that brings us to our idea of utilizing machine learning models for hydrogen production. And we have been actually getting good results. We are actually looking at utilizing inverse analysis and also multiple objective regression models so that we can balance off, like optimize hydrogen while reducing energy consumption, or maximizing hydrogen while reducing catalyst deactivation in our entire system. So, what challenges do we face? And the first one is one that has been mentioned throughout the entire conference so far: data availability. Data is key to programming any model, and this is something that is a stickler in our research, getting data that is of high quality and the quantity that we need. Also, variation in the data. We're all researchers. We report data differently. So having a standardized data set can present a challenge at times, because sometimes you look at your Excel sheet and you're going through 1,500 different lines of data, and then you see a lot of different variations. You now have to come up with a way. So the variation in the data, how it's reported, is also important. Feature selection. Now, understanding, and that's why when we do any model, we do a feature important analysis. Understanding what features play the most important role in this catalytic pyrolysis and also in a physics-informed neural network helps us understand how we can optimize the hydrogen production. And the changing in literature. Things we knew 10 years ago have evolved to what we know now. And because of that as well, data kind of evolves with it. So the future direction of our process is to improve our data set and quality, include additional input features such as catalyst surface area or particle size, looking at steam to carbon ratios within the process, and also the weight-hour space velocity and temperature changes. Comparing these multiple models and then validating them. So I can stand here and tell you our model will work, but how do you know? The only way we can do that is by validating these models with experimental data. So we're using experimental data to program our model, then validating them. But the thing is with machine learning, it gives us a better understanding of where to start and how to optimize this process. And that's where we can move from utilizing fossil fuel in the past to utilizing hydrogen in the future. As my little friend is walking there, we're disappearing. And by 2050, fossil fuel hopefully should be reduced in another 100 years. The depletion will be enough that we will have to find solutions. So why wait till then? As my colleague just mentioned before, there is hope and there is a pathway but through collaboration, that's the only way we can do it. So hydrogen does offer a competitive solution. And by using experimental data and machine learning model, we can enhance hydrogen production through catalytic pyrolysis, thus charting a new way and an energy transition for the entire Caribbean region. I would like to thank my research team and the MME department of FIU and University of Ghana. Thank you.